Shall I leave now?
Yes, sir. Okay, sure, sir. Participants, please fill the feedback form of this session. We have next session by Dr. R. Vinu, Professor, IIT Madras. Sir is yet to join. Please stay. Yeah, sir has joined. Vinu, sir.
Yeah, I'm leaving now.
Yeah, good evening, ma'am. Good evening.
Good evening, sir. So, shall we start, sir?
Yeah, sure.
So, participants, we have the next session of Atal FTP on sustainable engineering and carbon neutrality by Dr. R. Vinu. I'll just give a brief introduction about Dr. R. Vinu. Dr. R. Vinu, he is currently professor in chemical engineering department at Indian Institute of Technology, IIT Madras, Chennai. He did his BTech in chemical engineering from AC College of Technology, Anna University, Chennai, and PhD in chemical engineering from Indian Institute of Science, Bangalore in 2010. Prior to joining IIT Madras in 2012, he was postdoctoral research in Northwestern University, USA. At IIT Madras, he leads an active research group that focuses on thermochemical and catalytic conversion of diverse feedstock such as biomass, waste, plastics, algae, municipal solid waste, and coals to sustainable fuels, chemicals, and materials. He is also the director and co-founder of deep tech startup company X2 Fuels and Energy Private Limited, incubated at IIT Madras Research Park, that focuses on the conversion of industrial and municipal waste to fuels through hydrothermal liquefaction process to refinery blend stocks. He has executed many important applied and scientific projects of relevance, particularly to the industries such as Shell, ExxonMobil, Thermax, Tata Steel, Valmet, C6 Energy, Gas Authority of India Limited, GAIL, Chennai Petroleum Corporation Limited, HPCL, DHEL, etc. Dr. Vinu has published around 170 plus research articles in reputed journals with around 7,000 citations, 10 plus book chapters, and edited a book and 5 patents with an H index of 51. He has received many awards and honors. Some of his notable recognitions include he has received Professor N.R. Kollur Memorial Medal for the best doctoral thesis in Chemical Engineering Department, IIC Bangalore, Bhagyalakshmi and Krishna Iyengar Award for having guided the best MS project in the area of alternate energy. He's received Young Scientist Award, Dr. M. Anandakrishnan Prize in Engineering and Technology, the Academy of Sciences, Chennai in 2020, ICT Alkynes Amines Young Scientist Award by Institute of Chemical Technology, ICT Mumbai, has received Young Engineer Award, Institute of Engineers India, Keshav Ranganath Award for Best PhD Thesis Guidance, and NASI Young Scientist Platinum Jubilee Award by National Academy of Sciences India, INSA Young Scientist Medal, Indian National Science Academy, also Institute of Research and Development Award, Early Career Level at IIT Madras, and Amar Dai Chem Award for Excellence in Research and Development by Indian Institute of Chemical Engineers. He serves as one of the editors of Journal of Analytical and Applied Pyrolysis and in the editorial boards of Biomass, Bioenergy, Scientific Reports, and Frontiers in Fuels. So, with great pleasure, I welcome Dr. R. Vinu to take over the session. Welcome you, sir.
Thank you, ma'am. Thanks for the kind introduction. Is my voice audible and the screen is visible?
Yes, sir. Audible and the screen is visible.
Okay. Thank you. Thanks for joining this FDB program. I didn't recognize that the entire program is organized in the evenings. So, so glad that a lot of people are here. So maybe in the next 50 minutes to 60 minutes, I'll try to discuss on resource recovery aspects from waste for us from a circular bioeconomy viewpoint. And I'll also tell you how this really links to sustainability. So if you think of circular economy, okay, so what is circular economy? So the typical definition is that we try to make sure that the waste leakage into the environment is substantially minimized. So that means we need to make sure that we extend the lifetime of the materials and services that we use. Okay, so reuse is a very, very important concept, right? And it's also important that we remanufacture and refurbish, without really letting the use of items as a single-time use products. So a classic example is one-time use, single-use plastic is a classic example, wherein we are simply throwing it away, and that really results in waste in the environment, right? And ultimately, the last option, okay, these are called as the primary, secondary, and the tertiary, resource recovery options, wherein if nothing is really going to lead to any efficient recovery of materials or chemicals or the raw materials. So it's important that we do this recycling process. That means we try to really break the material, molecularly crack the material, and then make chemicals or fuels or some kind of different raw materials for the industry. So in effect, we don't really go with the take, make, use, dispose, pollute, which is the typical linear economy model. But we try to make sure that we extend the lifetime of the products. Okay, so the waste leakage is eliminated. So eliminating the waste leakage into the environment is really ideal scenario, but at least the starting point is to minimize the disposal of waste into the environment. So ultimately, the question is, can the waste derived bioeconomy or circular economy, can it be a potential solution to fossil based linear economy? Okay, this is still unanswered. There are a lot of challenges, which is what we will see. Okay, and what is a sustainable economy? Okay, if you think about a sustainable economy, okay, from let's say I take an example of the of what is a net zero pathway or the net zero goals that different countries have really agreed to, right? So we had different Paris Treaty and so on, right? So what it basically says is we try to make sure that the global average temperature rise is kept within 1.5 degrees, okay, by really bringing in a lot of strategy interventions. Okay, but there are also reports that say that currently even this has crossed 2 degrees. Okay, there are various reports that say that. Okay, so typically sustainable economy, okay, has to be in one view, right? It has to be bio-based, it has to be low carbon, and it has to be circular. Okay, so I see this circular economy as an intersection of bioeconomy, low carbon economy, and circular economy. Okay, that means we try to replace a lot of these fossil fuel derived materials by bio derived materials, right? We try to achieve low carbon intensity emissions in the various processes that we deploy, and we also make sure that the materials go through a circular pathway. Thereby, the lifetime of these materials are actually enhanced in our life cycle. So basically, right, you need to have decarbonization processes, right, reducing dependency. Okay, that is of course the ideal thing, right? I mean, a classic example is plastics, right? We use I mean, plastic is indispensable in our daily lives, right? But I mean, 99% of the plastics that we use today are derived from fossil fuels. Okay, waste handling has to be done by carbon capture, utilization, and sequestration, and then there has to be a reduced primary materials demand. That means we have to increase the circularity per capita. Okay, so if you think of the waste that each one of us emit, let's say a solid waste that each one of us emit into the environment, right? It is roughly about 0.5 to 1 kg per person per day. Okay, in India. Okay, so the estimates vary, but this is a typical waste disposal from our side. Okay, but we need to increase the circularity per capita. How much of the material reuse that we are really doing, so that we are actually lessening the amount of waste that is being rejected, right? And this means that we need to enhance the individual's responsibility. That's ultimately that's ultimate thing that we need to do, without which none of these will really work out. So how do we achieve decarbonization? So if you really look at the various industries, okay, so you might wonder why I'm talking about decarbonization here. So see, it is about circular economy, but I feel that circular economy is very much linked to the energy, okay, and waste and energy cannot be or should not be really delinked, okay, from each other. Okay, we need to really look at waste and energy as a single entity, or interrelated entities. Okay, so if you really look at the major industries that are really emitting CO2 into the environment, right, it is basically the heavy industries: cement, steel, and plastics, that is refineries. And in terms of heavy duty transport, it is predominantly the trucks, that is the road transport, due to diesel use, shipping, marine fuels, and aviation fuels. And all these put together contribute to about 30% of annual carbon emissions. Okay, and for example, if I just take one example of this aviation industry, right, because aviation is leading to a lot of CO2 emissions, and today there is a lot of talk about sustainable aviation fuel, or SAF, that many countries are really marching towards. Okay, so there are even targets set that by 2030, okay, there is going to be certain billion liters or certain percentage of SAF that is going to be incorporated into the fuels, aviation fuels. So if you really look at the SAF requirement to achieve net zero by 2050, 2050 is an ambitious target, right? You see that the amount of sustainable aviation fuel that must be produced is actually exponentially increasing. Okay, so today we are actually very, very low in terms of SAF production, but if we have to achieve net zero, we have to really go up to 450 billion liters of SAF all over the world. That's like a huge target. So this is typically the impact of the emission from the conventional fuels, and this is like a compensation that we need to make sure that we achieve decarbonization. So there are various roadmaps to decarbonization. Okay, so you can see the first thing is always reducing demand for carbon intensive products and services. So that means we need to have circular economy in the heavy industry. Thereby we can really make sure that we are able to reduce the carbon emissions by 40% in it, right? And similarly, right, if we are able to have efficient logistics here, right, we can still reduce our carbon intensity by 20% here, right? Improving energy efficiency is quite common to a lot of different process industries, where energy has to be monitored, energy consumption has to be monitored in different processes, and we need to make sure that the energy efficiency of the process is going to be improved, right? And ultimately, right, we need to make sure that we are actually able to move to, because we have renewable power that is very much accessible due to solar and wind, right? There is a possibility that a massive electrification can actually be done, and that can lead to substantial CO2 reductions. Electricity coming mainly from the renewables. Okay. Prioritize the use of biomass to make bio-based plastics and aviation fuels, or even transportation grade fuels. Incorporate carbon capture, right? And the last one is, of course, start. Already there is a lot of push around in India, especially, and in the EU, on the use of hydrogen, okay, as an alternate clean burning fuel, right? So basically, hydrogen is also one of the important things by which we can make sure we achieve decarbonization. And by the way, hydrogen can be derived through electricity or derived from biomass. So there are like different possibilities there. Okay, so this is like International Energy Agency's prediction, Okay, this is a parachute diagram here, which says that what has to be our targets to reach to achieve net zero by 2050. Okay, so you see here again, these are quite interesting things. Whether or not we achieve is a secondary point, but at least this is basically for you to understand that this is a very ambitious target. Okay, even though 2050 is quite down the line, quite some years down the line, 2 decades at least, it is still a very ambitious target. So you can see that if we have to achieve net zero by 2050, right? No new sales of fossil fuel based boilers, okay, by 2025. Is it really happening? No. Okay, 60% of global car sales must be electric. Okay, there should be about 720 gigawatts electrolyzer capacity has to be ramped up, right? Simultaneously, the emissions from cement industries have to be captured and stored to the tune of 8%, right? By 2035, no IC engine car sales should happen, no petrol or diesel based cars. Everything has to be, let's say, electric or hydrogen based, right? 2040, 50% of existing buildings should be retrofitted to zero carbon ready levels. That means electricity is going to be a major player in the industry energy consumption. 2045, no IC engine trucks, and everything has to be electrified trucks or by hydrogen, right? And finally, you have only the electrolysis, playing a major role. So whether these are really possible or not is not the real question, but this is really for you to understand. When targets are set, right, there are always challenges that need to be met, and the policies also have to be in place to make sure that these are done. So, this diagram clearly tells you that, today we are supplied, the energy comes from coal, natural gas, and oil, right? But if you are expecting to be in a very ambitious scenario, right, in 2050, right, low emission sources such as nuclear, hydro, bioenergy, wind, solar are going to be the real players. And this is just a split up according to the different industries. Broadly, you can classify as industry, transport, and buildings. Okay, so when we are talking about a waste, right, bioenergy, that's where the bio-based waste, okay, which could be biomass, sometimes even waste plastics, right, can play a very important role. Okay, so if you just take about bioenergy, you can see that already, it can really play a major role in as a raw material for chemicals and feedstocks. It can play a major role in aviation fuels, shipping fuels, right? It can be used for bioenergy, wherein you combust biomass to make electricity, power, right? And even in many other industries like cement and steel, you can really make this biochar, and this biochar can actually be a source of alternate carbon. So you can see that, right, biomass can contribute in terms of direct use of bioenergy, for electricity generation, for chemicals, for biogas for electricity generation, and biogas for hydrogen generation. So in different forms, bioenergy could really could actually provide substantial amount of energy to meet our needs. And what are the different technologies, and whether they have a major role or a minor role? Already you can see that hydrogen has an important role in cement, steel sector, plastics making, because plastics need, if you want to make a plastic, hydrogenation is an important step, right? Road transport, hydrogen can play a major role in shipping, right? And of course, electricity, biomass based electricity can have a major substantial role in the cement industry, right? And obviously, you can also see that, right, ammonia can play a major role in shipping, right? So you can see that typically for dispatchable zero carbon power sources, like hydro and nuclear, biomass can be easily a competing raw material. Okay, from the Indian context, if you see, right, the energy is actually increasing on the one side. Sorry about it. Yeah, energy is increasing on the one side, 2025, 2030, 2035, right? still, I mean, the predictions basically say that, it is going by how the policies are being adopted, right? Still, coal, gas, and natural oil and natural gas are going to be the major players, but still, you have the renewables, nuclear contributing only a very, very small fraction to the mix. And on the other hand, of course, these are slightly older prices, but you can basically see that the oil prices also due to the geopolitical tensions tend to vary, right? And basically, we are an oil importing country, so that means it's important that we look for alternatives to meet our energy demand, chemicals demand, and fuel demand. So, talking about renewables and waste, one important renewable or biomass is a lot of these agro residues. Being an agrarian economy, it's important to recognize that a lot of agro residues are being available in India, right? This is in addition to using them for as a fodder for cattle. So this is a surplus residues that are available, right? And every one of you know that open field burning is such a common practice in the northern India, but also in other parts of India to a very less extent. But that basically results in pollution, loss of a lot of nutrients, a lot of nitrogen from the soil, a lot of phosphorus and potassium from the soil. So already there are reports that say that the our soil carbon content has actually reduced by half. Okay, so that also means that we need to protect the soil to make sure that right, and that's where biochar today is becoming a very, very important topic. Okay, and there are always other different sources: municipal solid waste, animal residues, forestry, agri waste, and so on. Agri residues, of course, the major component of the waste, and typically we are talking about second generation raw materials like lignocellulosic agro residues. But one can also think of, I mean, this is not a conventional notation to call it Gen 4, but I usually call the municipal solid waste as probably a generation 4 feedstock to make different types of fuels and materials. So from a waste generation point of view, right, the waste generation varies by economy, varies by the lifestyle of people, right, by the income level, right, and also by region. Okay, so typically, and the waste management practices also differ. Okay, so if you look at the low income countries, predominant mode of waste disposal is by open dumping, whereas high income economies, I mean, they claim that they have they do a scientific landfilling, they do recycling, and they also do incineration in a very controlled way, right? Of course, these are debatable. There is also a trans border, or I mean, there are also waste that are being shipped to other countries. We are not talking about it here. That's kind of a sensitive thing, but still, I mean, these are at least as per the statistics. Okay, and what about energy and value from waste? That is certainly the way to go, right? It is important that, of course, in the first place, it's important that we as citizens have to segregate the waste before dumping it, and that also requires very strict policy interventions, right? But at the same time, if you look at the waste management, the waste profiles in different cities, again, this is just a snapshot from Tamil Nadu. So you can see that in Trichy municipality, one of the municipalities, you can see that organic waste is about 32%, but then other fraction of waste is quite significant, right? So you have garden waste, paper, plastics, right, coconut shell, cloth, slit, tires, wood, right? So many different fractions that constitute, and if they are not really segregated and disposed of in a proper way, that could lead to disposal in landfills that are really growing tall. And there are many other socio-economic issues that occur because of these unscientific way of disposal, or landfills that are really becoming dump sites. Okay, because landfilling itself is a technology or a technique or a science actually, and the way you landfill it, you monitor it to make sure that you convert it at a later point in time to your real estate. I mean, it's a very long time process. But today, landfills are being simply biomined. There is a leachate that is causing harm to the water bodies because of this. So there is a lot of issues that pan out, okay, because of this landfills not being properly managed, but really being used as dump sites. Okay, so let's talk about plastics again. If you really look at the plastics, predominantly packaging industry contribute to major fraction of plastic waste, right? In fact, even if you look at the plastics that are being made, almost 36% is towards the packaging industry, right? Only other fraction contribute always lower than the packaging industry. And everyone knows the basic type 1, 2, 3, 4 up to 7 type 1 to 7 classification of plastic according to Society of Plastic Industries. And if you look at per capita, on a per capita basis, we are probably doing much better than other countries in the world. But in terms of the quantum, we are actually increasing. Okay, this is about the total plastic packaging waste, not the total waste. But if you just look at the plastic packaging waste, I mean, we are on a per capita basis, we look better. But in terms of the actual volumes, we are not. I mean, this is still 2021 data. Okay, and one of the biggest advantages of having plastic is because they are derived from hydrocarbons, they have a very good calorific value. So it's quite easy than compared to a lignocellulosic biomass. It's quite easy to convert plastics back to any kind of hydrocarbon derived fuels or fuel oils. And one important point is, besides the 7 categories of plastics, I mean, in India we also have the EPR guidelines. That's actually very nice, where plastics are classified into 4 categories, different category, wherein you have category 1 is rigid plastic packaging, usually made of HDPE and PET. Category 2 is flexible plastic packaging of single layer or multi-layer. Category 3, multi-layered plastic packaging, at least 1 layer of plastic and 1 layer other than plastic, like aluminum foil and other things. And category 4, which is a plastic sheet used in packaging as well as carry bags made of compostable plastics. So again, this is another adding another layer to the plastic sorting and the extended producer responsibility coming into picture to make sure that plastic disposal is very well taken care of, and it also gives some kind of a binding to the industries or companies that use plastic as a part of their packaging or even their product. Okay. So ultimately, right, just like a water cycle, hello, am I audible?
Yes, sir, you are audible.
Okay, just want to make sure. Yeah. So just like a water cycle, a carbon cycle, right, today what is also emerging is a plastic cycle, or sometimes it's also called as a microplastic cycle, because plastics are becoming a very important component, right, in all parts. Even human body, every part of our human body is has been identified to contain some plastic, right? So microplastics or nanoplastics. So if you look at the complete plastic cycle, this goes like this, right? So you have the fossil carbon that is being used to make plastic by the refineries. Then it is being used, it is disposed, right? A part of it goes to energy generation, and that results in greenhouse gas emissions. Or you landfill this plastic, and that can result in leachates that can actually percolate and contaminate the groundwater, or even the leachates through some wastewater treatment can go as an effluent. And obviously the ocean plastics, because they spend a lot of time in the plastic saline water, it can actually lose its properties. It can actually break down into millions of microplastics, nanoplastics, and finally dissolved organic carbon. So this is more like a plastic cycle that we can think of today. So overall, if you see, waste management really unites 14 of the 17 sustainable development goals through a cross-cutting opportunity. So, I mean, this is quite self-explanatory here. So, right from 1, 5, 8, 10, okay, to empowering women, to circular economy that can really promote 7, 9, 11, and 12, very, very important and directly related UN SDGs. And overall, it can actually result, enhance, better, lead to the betterment of life on land, life below water, climate, right? It can ameliorate the climate, extreme climates, clean water, good health, and finally, obviously, partnerships are important. The global partnerships are important to achieve some of these goals. Okay, so this is just to give you a background of where we stand with regard to waste. What are the different? I've probably given you an outline to what are the different waste and why is it important, some statistics and things like that. Now let's move to probably a second part of my talk, wherein I'll be focusing on what we do in our group and things that are very much related to waste management. So we deal with a lot of different raw materials, lignocellulosic biomass, agro residues, waste plastics, unsegregated MSW, lignin, methane, carbon dioxide, and so on. And we apply different processes to convert these raw materials into valuable products. So we apply pyrolysis, combustion, hydrothermal liquefaction. We use non-thermal plasma. It's a process, and then we also use catalytic techniques like hydrogenolysis and so on. And ultimately, we try to gain a better understanding of the processes by applying some time resolved data. We use different hyphenated techniques to understand the reaction mechanism and kinetics, catalysis, and we also do some process development and scale up. Not everything, but at least the best candidates, we try to scale it up to a larger scale. So the underlying questions that we always try to answer are: can the waste-based bioeconomy, can it be a potential solution to the fossil-based linear economy? And is it really sustainable? Sustainability is not just about a process, whether we are able to achieve something by replacing fossil material with a biomaterial. That's not just about sustainability. Sustainability is cross-cutting. The process has to be sustainable, right? The raw materials, the products have to be sustainable, right? The environment, okay, should not, the new process or the new raw material that you're using should not really harm the environment in terms of the byproducts that they generate, right? And sustainability is also linked to socio-economic, okay, socio-technical, socio-political, right? And it really cuts across various disciplines. So what we do in our group, one major aspect that we focus in our group is try to really convert a lot of these different waste to liquid fuels. Okay, so converting any kind of a raw material to liquid fuel is challenging, but this is something that we want to do because liquid fuels can be stored, they can be easily transported, and they can also be upgraded, to better fuels, and they can also be you can also make fine chemicals and valuable intermediates based on the raw materials. So we basically mapped the different techniques that are used to convert different types of raw materials to any kind of a liquid fuel. It's not that we make the same liquid fuel from different raw materials or processes, but something that is a liquid. Okay, so that's our big picture goal of what we try to do. Okay, so coming to raw materials, right? It's important to understand that the raw materials, vary. The properties of the raw materials vary in a very wide range. Okay, so that means if you look at, so here these are the basic characteristics of any raw material that we might want to understand. Okay, moisture content, what is a volatile matter? Okay, this comes from the proximate analysis. Then coming to elemental analysis, what is the carbon, hydrogen, and oxygen content, and then what is the calorific value, higher heating value of the raw material. So the challenging aspect is, if you talk about, let's say, biomass, even if you consider woody biomass, right, the moisture content can vary widely. Okay. Similarly, if you take, for example, if you take a manure, right, the moisture content is going to vary substantially. So, and even the volatile matter in a typical woody biomass can vary in a very wide range. Okay. So, so the challenge with biomass is, biomass or even MSW here is that, I mean, the properties vary over a very, very wide range. Okay. So it's going to be very, very difficult for you to tune a process to a specific, tune a process to specific parameter set or range, because everything is dependent on the raw material that you are processing. Okay, and so does the product yield and quality. Okay, from different technology platforms. Okay, so here you can see different processes. I mean, typically you do a process, you get solid, liquid, and gaseous products. Okay, which could be used as fuel. So you can see that I mean, different processes actually yield your products, or the product yields vary in a very, very wide range. And if you're able to plot the effective hydrogen to carbon ratio with respect to calorific value, you can actually see that all the liquid fuels made through different processes, be it pyrolysis or hydrodeoxygenation, okay, actually lie in a very, very broad range. Okay, so what I mean to say is raw materials determine the type of products formed, and so does the technologies that you use. Okay, both these are going to really play an important role in determining the yield and the quality of your products. So first, coming to let's say the pyrolysis process. Okay, I mean, again, in the interest of time, I may skip some slides, but I would like to just focus on certain technologies, so that I mean, at least the understanding is clear on some aspects. So pyrolysis is a process wherein we try to heat the material to high temperatures in the absence of nitrogen. That's a very simple description of it. But more importantly, and more technically, right, pyrolysis is a process that can actually be used to tune the product distribution. Okay, whether you want high amount of liquid or biochar or gases, everything can be achieved provided you are actually able to tune the operating conditions. And what are the operating conditions? Right, it's all about your pyrolysis severity. Okay, temperature and residence time, okay, really controls the yield of products you get from pyrolysis process, and that occurs through a set of primary reactions and a set of secondary reactions that occurred during pyrolysis. So, for example, if you take biomass, right, typically the primary processes result in the generation of liquid aerosols and gases. And if you're going to have a longer residence time or a higher temperature, right, that can actually result in the secondary transformation of these primary pyrolysis vapors to condensed oils, phenolics, and secondary char. Okay. So typically in a thermal degradation process, what happens is the material that would contain moisture, physisorbed moisture, gets released, and the material basically decomposes into tar, gases, and char. And secondary pyrolysis, you have a lot of these reactions like reforming, dehydration, cracking, occurring simultaneously to make to change the composition of the products. Okay. So if you think of plastic pyrolysis, I'll probably cover plastic pyrolysis today. If you think of plastic pyrolysis, actually it's not a new subject. A lot of it is known, and it is well proven that, for example, from olefinic plastics like high density polyethylene, low density polyethylene, polypropylene, polystyrene, you can actually get very high yield of oil that is actually rich in hydrocarbons like aromatics or aliphatic hydrocarbons that can be seamlessly blended or upgraded to liquid fuels. But with some plastics like PET or polyvinyl chloride, okay, those are not really the good plastics to be pyrolyzed, because, for example, PVC pyrolysis results in a substantial amount of HCl vapors due to dehydrochlorination reactions. So it can actually result in toxic fumes, and it can be an emission problem, right? And whereas PET does not degrade well during pyrolysis, okay, but it's a very highly recycled polymer in the world. So different polymers decompose in different temperature regimes, right? And it's first important to understand the typical decomposition temperature of the polymer before devising a pyrolysis process. Okay, and typically the properties of the pyrolysis oil, if you take, this is also reasonably well documented. Okay, so compared to, let's say, diesel, you can say that polypropylene or HDP, LDP oil is quite close to the properties of diesel, right? And not only in terms of the calorific value, but also in terms of other properties like, let's say, the cetane number, port point, and so on. So I would just like to give you an example of one type of waste plastic resource recovery that we did, wherein I mean, if you consider a typical COVID scenario that we faced, right? We were actually using a lot of this PPE kits, waste PPE kits, that actually includes coverall or simply a face mask, gloves, and so on. Right. It was at that time, when the increase in biomedical waste actually rose by about 10 times because of excessive use of these COVID PPE kits. Right. And if you go by the typical environmental laws, okay, I mean, biomedical waste are actually supposed to be incinerated. Okay. So whether it has contaminants or not, the moment it is coming out of a hospital, okay, it has to be the treatment is basically autoclaving, microwaving, right? And you are not supposed to really do any landfilling. Okay, and even recycling is not actually a CPCB approved process. For example, if you take the yellow bag materials, right? So those are supposed to be incinerated through plasma pyrolysis or incineration. Okay, so there are laws. Okay, but if you really look at a typical PPE kit, it is also important to understand what this PPE kit is made of. So if you look at it, if you take a typical PPE kit, this is a study that we did. We tried to really rip off the complete PPE kit to understand what are all the different components that are made of, what polymers make the PPE kit. So you can see that if you take a simple surgical mask, right, you have some layers of surgical mask, you have ear strips, you have nose strips in it, right? And this is a body coverall, right? You have a safety goggle, nitrile gloves, right? And if you take an N95 mask, that's also containing multiple layers of N95 masks and so on. And a face shield contains so many different things. So we use pyrolysis as a technique to identify the polymer, and at the same time, we try to use it as a process to make sure that we are able to decompose the polymers into different valuable products. Okay. So if we really looked at the mass distribution of the polymer from a PPE kit, we found that polypropylene, PET, and polycarbonate, okay, really constituted about 95% of the mass of the PPE kit. Okay, because a lot of this is made of PPE, right? The entire coverall is made of polypropylene. The mask is made up of polypropylene, right? And your face shield is made of PET, right? Your safety goggles are made of polycarbonate. Okay, so you can see the typical distribution of the plastics in a typical PPE kit, and this is an identification that we did. We tried to identify each of these materials as let's say nitrile gloves or PP, PC, and so on. Okay, based on a pyrolysis analysis, we try to understand, based on the nature of the products, we try to understand what is the polymer from which we got these products, right? And what we also do is we do a lot of catalysis work, right? We try to evaluate what are all the pyrolysis products, but then we also try to modify the pyrolysis products and see if we are able to derive some valuable chemicals, as I said, chemicals, or in this case of a coverall suit. Okay, this is the coverall suit. If you see, right, without using a catalyst, we get some alkenes in different carbon number ranges without any specificity. But then we try to use different catalysts like zeolite Y, ZSM5 at different. We do some optimization of the temperature and the catalyst loading and other things. What you see is ultimately we were actually able to get benzene, toluene, xylene, and ethylbenzene and naphthalene as the major products in the product distribution. Okay. This is important because, for example, if you think of the petrochemical, the major petrochemicals are benzene, toluene, xylene, which is used as octane number improver in gasoline mixes. Okay, so this is one of the important applications of making BTEX. If you take other polymers like PET, okay, PET is a polymer that is widely recycled, okay, in the world. Okay, but pyrolysis is as a resource recovery or a recycling strategy is not actually good based on literature. It's not a very good process for PET recycling. But what we observe here is by using some catalysts, we are actually able to improve the yield of product like benzene as a simple chemical from PET. So we get benzene, toluene, xylene, okay, as the major products, and the benzene yield was quite higher in this case. But without using a catalyst, you see that you will make acetophenone, benzoic acid, right, biphenyl, right, which are which are basically the depolymerized products of PET. Okay, because PET is an oxygenated polymer. It's not like polypropylene, which is only a hydrocarbon. Okay, it's an oxygenated polymer, so degrading it would result in oxygenates in the products in the product distribution, right? Then we even have studied more complicated mixtures, like for example, this is a multi-layered plastic packaging for hydrocarbons. Okay, so you can see we tend to actually dispose a lot of these plastic packaging waste every day. Okay, so it's important that we actually make sure that these multi-layered plastic packaging waste are carefully disposed and properly recycled. So in terms of these plastic packaging waste, so here we took let's say 4 different MLPs, multi-layered plastic packaging waste. Okay, so here we do a simple analysis, FTIR analysis, where you can actually see that one layer of the MLPW, this is inner layer, is actually showing the characteristic of polyethylene, whereas the outer layer, outer cover of the MLPW is actually showing the characteristic of PET. Okay, and obviously these 2 layers are bound together by using some kind of adhesives, okay, which are also used in the in making of these plastic MLPWs. Okay, and when we did a basic basic TGA analysis, we could see that there are 2 specific decomposition regimes. Okay, one regime corresponding to PET and the other regime corresponding to HDPE decomposition. Okay, so this is a very basic characterization to understand what this is made of, and then we try to do a pyrolysis study of it to understand what are all the different products we get out of it, and then whether we can really make anything useful out of it. So here, when we do a non-catalytic pyrolysis, we get typical characteristics of polyethylene decomposition without any specificity So selectivity is always the key in a lot of these processes. Okay, it's not about how much conversion you're achieving, but it's all about how much selectively you're actually able to make a specific product. So in this case, with ZSM5 catalyst, we could make benzene, toluene, xylene, ethyl benzene as the 4 major products from this MLP. Okay, so here you can see again we do some optimizations and we got maximum of about 16% yield of just these 4 products: benzene, toluene, xylene, and ethyl benzene from MLPW. Right, and we also try to extend this to scenarios where plastic cracking is also accompanied by contaminants that may be present, which could be biomass. Okay, and that resulted in a lot of our studies focusing on co-pyrolysis of biomass and plastics. The fundamental idea here is that biomass is oxygen rich, plastic is hydrogen rich. If you do only biomass pyrolysis, it would result in oil which is going to contain a lot of oxygen containing molecules, and so if you are going to blend it with plastics, it could marginally improve the yield and quality of the product. So we have done a lot of studies. This is one of it on microwave assisted pyrolysis. We developed this microwave assisted pyrolysis in our lab. We worked on it for different systems, right? And here we see the example of rice straw, bagasse, polypropylene, polystyrene, where we studied the individual samples as well as the mixtures, right? And what we find here is this is a co-pyrolysis results, where you can see that blending rice straw with polypropylene is basically going to improve the calorific value of the products. Okay, the flash point is going to come down substantially, right? You can see that the viscosity of the oil, which was higher with biomass, has been reduced to something in the light fuel oil range, right? And the density typically with polypropylene mixtures is typically in the diesel range, right? And viscosity is a very important point here. Not only viscosity, but also the stability of the oils. Okay, typically the oil stability is determined by the molecular composition. So if it has a lot of oxygenates, then the stability is expected to be poor, because the oil can polymerize over time, and that can lead to viscosity even increasing with respect to time. Okay, whereas blending of plastic can really help in terms of moderating the viscosity of the oil, so that it can be used for it can be stored over a longer periods of time. So what happens during biomass plastic co-pyrolysis? Okay, so this is a typical scenario. So you take a biomass, only biomass pyrolysis results in a lot of these oxygenates. In fact, we observed all these things in our studies, right? And if you're now going to blend a biomass with plastic, right, that would result in co-pyrolysis vapors, okay, which are not heavily oxygenated, but still oxygenated. It would contain a lot of alcohols and so on. But now if you are now going to co-pyrolyze this with respect to using ZSM5 catalyst, right, and that can really result in deoxygenated vapors, which contain a lot of hydrocarbons, deoxygenated aromatic hydrocarbons, and some amount of oxygenates, which are mostly long chain alcohols. So if you look at the Peona distribution, that is paraffins, isoparaffins, olefins, naphthenes, aromatics, a typical refinery fuel analysis, right, you will see that this oil contained predominantly aromatics and olefins, but these are mostly the aromatic hydrocarbons that are derived, that are shown here. But the higher carbon chain length molecules are mostly olefins, naphthenes, and some amount of paraffins, which were present here. Okay, we also extended this to plastic mixtures. Instead of biomass plus plastics, we have also done a lot of studies on plastic mixtures. Okay, so here you have polystyrene, polyethylene, polystyrene, polypropylene, and polystyrene, polypropylene, polyethylene. Okay, this was a part of a bigger UK-India project. Okay, wherein some of these oils were also blended with diesel engines and tested. for the performance of the diesel engines. So you can see that again with a tri-component mixture at 1100 watts, slightly higher powers using ZSM5 catalyst, we could actually get typically the products in diesel range, but still it is not a diesel fuel because aromatics are high. Okay, because you have polystyrene results in aromatic hydrocarbons in the oil, right? And then if you go with something like a paper mill waste, cellophane, right, that would result in a lot of other oxygenated compounds as well. Okay, so we have done multiple things, right, wherein we have used food waste digestate, AD, anaerobic digestion pyrolysis oil with biodiesel. We blended it, and we have also shown that it exhibits marine fuel like properties. So and this has also been extended to many other cases. I'll just present very quickly some of the cases here. So one is we have used the crude oil sludge that is going to be collected in the bottom of the crude oil tanks in the refineries, and we have shown that using microwave pyrolysis and zeolite upgradation, we can make diesel grade hydrocarbon fuels containing mostly paraffins and isoparaffins, right? Again, through pyrolysis, I mean, these are some of the exploratory stuff. Without, I mean, for example, this nanomaterial production from biomass, especially with high ash containing biomass, is not really a commercially viable thing, but at least as a proof of concept, we have shown that using some iron and cobalt can actually result in some nanostructures in the biochar, or using lignin, you can actually make phenols in very high selectivities, and you can also convert activate the pyrolysis biochar that is derived from microwave pyrolysis can be activated to make more porous nanostructures, high surface area materials that can be used for absorption of dyes from wastewater. So we have done a lot of these kind of studies using pyrolysis. So maybe in the next 10 minutes, do I have 10 minutes, ma'am? Another 10 minutes?
Up to 9 o'clock, sir.
Okay, I'll try to close in 10 minutes so that if there are any questions, we can take it.
Yes, sir, sure.
So the next topic is again on on a slightly different technology called as hydrothermal liquefaction, which we are working over the past 6 years. So generally, if you think of pyrolysis or combustion or gasification technologies, one of the major requirements is your raw material has to be reasonably dry. Okay, that means the moisture content in your raw material has to be limited to 10 to 15%. If the moisture content is more, then you are actually spending a lot of energy to simply dry away the moisture from the sample. Okay, which is actually an energy intensive step. So our next question was whether can we really make liquid fuel, because liquid fuel is always our focus, from wet waste. Okay, for example, if you take a vegetable market waste, if you take a food waste, okay, these contain very, very high moisture levels. Okay, even more than 50-60%. It can we use them and then make some fuels. Okay, so this actually led to the process called as hydrothermal liquefaction, wherein it is a process that mimics nature's way of making fossil fuels by applying high pressures and temperatures. So typically for chemical engineering people, I mean, this is a phase diagram of water, where you can see that at the critical temperature, which is 374 degrees and 22 megapascal, right? Water is beyond this temperature. Water is going to exist as a supercritical fluid, right? At these conditions, if you plot the if you see the variation of density, dielectric constant, and ionic product of water, you will actually see that the density of water is actually going to be around 350 degrees. The density of water is very, very much similar to organic solvents, right? Its dielectric constant is not the same as water, H2O, but it is much lower. and the ionic product is very high. So that means water is not going to exist as H and OH. It's going to exist in the form of hydronium ion, H3O plus and OH minus. And that can result in a lot of redox reactions. So your organic molecules, organic polymer molecules, or even plastics can be decomposed at under these conditions. So we typically operate at a subcritical condition. We don't go to supercritical condition, but we operate at a subcritical condition within 200 bars and 350 degrees. And we try to actually make a product that is going to be rich in oil. Okay. So, so typically it's a very it's very natural to say that it mimics nature or the geothermal conversions. Okay, the salient features are feedstock agnostic process. I'll actually talk about a lot of these in the coming slides, right? And in a typical process today, we have actually scaled this process up to TRL 6, right? Wherein you know, we do HTL, we derive the product, right? We do a lot of energy integration, right? And we also use this biochar to combust and provide some process heat. Ultimately, we make oil, char, and char as the major products of this process. Okay, what are the applications of the product? So, I mean, the process itself can work with a wide variety of feedstocks, as I said, and typically the crude oil, it's more like a crude oil, hydrocarbon crude oil, but it's not really a hydrocarbon. It will also contain some oxygen and other molecules because it is derived from some agri waste and industrial waste and so on. Okay, so we are actually making some drop-in fuels, right, and which can directly be blended with crude oil, can be fractionated, it can be upgraded mildly by doing some cracking, right, or it can be made into bioplastics, biolubricants, and so on. You get biochar, which can be simply combusted for energy applications, or it can be used as a soil amendment. And you also get wastewater because typically you use about 80 to 90% water. So the raw material is going to be in the form of a slurry. So you get product water, which can actually be used in agri applications, or it can be used for anaerobic digestion water, right? Or it can also be recycled in the process. So initially I talked about a pyrolysis technology, and now I'm talking about HTL technology. Okay, which one is better? Okay, if I'm going to talk about converting you know, biomass or agri residues or biogenic waste, biodegradable waste, okay, HTL is better because the HTL crude oil has a better carbon content, lower moisture, lower oxygen, and so it has a better calorific value, okay, than pyrolysis bio oil. But the downside is, you know, the viscosity of the oil is going to be quite high. Okay, so there are ways to handle it. There are ways to reduce it even during the process by having some additives. Okay, but I mean, just if you do a apple-to-apple comparison, this is how it looks like. Okay. So this is just about the different raw materials that we have tested in our lab, from municipal solid waste, dry straw, industrial waste, black liquor, lignin black liquor, polycarbonate, macroalgae, seaweeds, and so on. We have actually scanned a wide variety of feedstocks. In fact, a lot of these works were done by my student Hari Shankar, who also happens to be from TKM College, Kollam. So he did a lot of these works that I'm presenting here from HTL. Okay, this is just about some results from municipal solid waste HTL. So this is a typical shredded RDF for refuse derived fuel we collected from MSW sorting center in Chennai, and I mean, these are all batch reaction test. You can see that here we also used some amount of glycerol, which is a biodiesel industry waste, as a co-solvent to actually improve the yield of the crude oil, right, which actually contained calorific value which is better than the pyrolysis oil. Okay, so overall, I mean, we have now we have even scaled it up to a bigger level, but typically I mean, the energy content of the product is going to be much higher than the energy of the raw material and the heat that you really provide to the system. Okay, so that is the bottom line. We have worked with rice straw. Okay, this is using again methanol as a co-solvent, not really ideal, but again, this was a part of our research activity where we got very good quality of the oil with using methanol as a co-solvent. But you can also use other catalysts like typically potassium hydroxide, sodium hydroxide, right, carbonates, because the use of these kind of homogeneous catalysts, these are not heterogeneous catalysts, they dissolve in water. So the homogeneous catalyst can actually improve the decarboxylation, that is removal of carbon. Oxygen in the form of CO2 is the main step in HTL process. Whereas in the pyrolysis process, CO, that is CO removal, is the major step. Okay, so now you can easily try to understand which is why HTL is better, because for every carbon removed, you are actually removing 2 oxygen, right, in the form of CO2, whereas in pyrolysis, predominantly for every carbon you remove only 1 oxygen. Okay, this is just one way to understand why oxygen removal is more in HTL, which actually results in better calorific value of the product. Okay, some products that we got from HTL of rice straw. We have also done a lot of process intensification strategies. Okay, that's what I said about aqueous phase recirculation. So you do this process, you get the aqueous phase. Can you really recirculate this back to the process in the next step, right? So that in a continuous process, you can think of recycling the aqueous phase into the process. So this was actually not very favorable for rice straw, because the crude oil yield decreased and the biochar yield increased, and that fundamentally was due to the release of potassium and chloride species from rice straw, because rice straw is a complicated biomass because it contains potassium and chlorine in it in the form of inorganics, right? And during HTL, these species gets transferred from the biomass solid phase to the liquid phase, and this is actually playing a deterring effect on the production of the oil. Okay, and we have also tried to use different things like tap water, wastewater, industry wastewater. Okay, this is recycled wastewater from IIT Madras. This is industry wastewater and even seawater, to understand how the product yields would look like. So again, just like pyrolysis, where you can vary the temperature and residence time, even in liquefaction, even in hydrothermal processes, you can do liquefaction to improve the crude oil yield, and you can also do carbonization to increase the hydrochar yield. Okay, so carbonization, we basically operate at low temperatures of 200 degrees and 70 bar and 4 hours. Whereas liquefaction, we operate at a higher temperature of 350 degrees, 180 bar and 30 minutes. Short time, high temperature. Here, this is low temperature and long time. Okay, so it's very similar process. Okay, but this results in hydrochar, which has different characteristics. So here you see that using different types of water, we got up to 75% yield of the hydrochar from rice straw. Okay, just to wrap up, see, if you are going to compare the quality of the oil with different types of fuels, okay, where do we really stand? Okay, so if you think of plastic oil derived through HTL, okay, so the calorific values are very high and comparable with diesel, crude. Okay, the oil from MSW HTL will contain a lot of oxygenates, right? But it has to be upgraded. So here you can see the oil that we derived from industrial oil, industry waste, was actually upgraded to contain a lot of paraffin. So we were able to improve the calorific value from 33 to 41. Okay, so obviously, right, by tuning the product composition, that is typically the elemental composition and the hydrocarbon composition of the products, right, you can actually achieve much better quality of the product. So if you look at it here, this is an overall comparison. So here you have HTL oil, this is distilled HTL oil, then you have pyrolysis oil, okay, then standard fuels like light fuel oil, heavy fuel oil, diesel, marine fuel, lubricant oil, crude oil, right? So you see here that the density of HTL oil is much better than pyrolysis oil. I mean, closer to the diesel range, whereas this is very heavy, right? You can see the flash point of the HTL oil. I mean, again, here it is similar to marine fuels, because marine fuels you need at least 60. And then you can see that the viscosity is lower and probably similar to marine fuels. Okay, calorific value is not as high, but at least much higher than pyrolysis oil and so on. Okay, so again, one-on-one comparison of processes is also important, and of course, overall, you have to look at processes from a techno-economic and life cycle assessment. Again, which I'm not actually presenting here. And we are also converting a lot of our batch processes to continuous processes through our startup company also. So we have a 100-liter batch unit in IIT Madras. These we are building now in IIT Madras Discovery Campus, and this is an operational unit in an industry in Chennai. Okay. So with this, I think I would like to close my talk. Okay, of course, I would like to have some discussions from your side. So effective solid waste management is, tightly coupled with energy. Okay, this is one bottom line or take home I would like to tell you. Okay, and viewing them in tandem, okay, helps us achieve SDG 7, which is affordable and clean energy and sustainable cities and communities. Okay. You can't decouple energy and waste. Okay, so when you're planning for renewable energy or energy self-sufficiency, it is also good to consider energy that you can derive from wastes. Considering the large quantum of waste generated, multiple technology solutions must be considered. Right, techno-economic assessment is something that's very important, and right, feedstock supply for pyrolysis technology is always a challenge, and HTL is basically an emerging technology that I think I have presented over the past 10 minutes. So with this, I think this is a big thanks to my group members who have really helped over the years to accomplish a lot of things that we have done. And thanks to the funding agencies, a lot of industries that really supported our endeavors in thermochemical conversion research. So with this, I close my talk now, and I'll be happy to take any questions and discussions.
Thank you, sir. Does the participants have any questions? Can ask right now. You can type the questions in chat window as well. Maybe sir.
Hello.
Yeah, one question.
Is there any possibilities to improve the heating value of the fuel? Is there any process in there?
Yes, sir. We can. I mean, processes are there. Typically, to improve the heating value, we do catalytic upgradation, wherein we try to further reduce the oxygen content in the fuel by doing hydroprocessing and other steps, which is quite well understood from a refinery perspective, because they are experts in hydrodesulfurization, hydrodeoxygenation, and so on. So we have to do that catalytic upgradation.
Is it possible to convert this pyrolysis fuel into as same as the diesel fuel?
Yes, certainly. That's what. See, if it is, if you are considering a pyrolysis fuel from plastic, it's quite easy. Okay, something like a mild hydrogenation will be much effective to convert it. But if you are deriving this pyrolysis oil from biomass, then you have to do greater extent of deoxygenation using catalysts. but certainly it is possible. As it is good. It is as good as a fuel oil. Okay, it is if you don't do any upgradation, right? The pyrolysis oil, let's say from plastics, can be used as a fuel oil by blending it with the conventional diesels, or it can be used as a blend with fuel oil. I hope that answers your question.
Yes, sir. Mostly this pyrolysis oil having higher auto ignition temperature or lower auto ignition temperature. How about its last point, fire point and all? Its auto ignition temperature, it will be higher or it will be lower? How close to the diesel fuel?
Okay, so the auto ignition temperature would be it would be lower, actually, lower compared to diesel.
I'm asking much closer to diesel engine application, whether it's having any knocking problem related to diesel engine.
It will have. Again, that is what I would like to be very clear at this point in time, that this pyrolysis oil derived from plastic, it will be closer to diesel oil. Okay. Pyrolysis oil derived from any agro residue or waste, food waste or anything like that, that will contain a lot of oxygenates, it will contain a lot of organics, so its properties will be quite different from a typical diesel oil. Okay, diesel fuel. So there you can actually see that it will contain a lot of low molecular weight volatiles that will reduce your auto ignition temperature and so on. So please be mindful of what is the raw material from which the waste oil is being considered. Pyrolysis oil is being considered.
Sure, sir. Thank you.
Vishnu S. Nair has raised a question. Vishnu, you can unmute and ask. Vishnu S. Nair. Is there any other participant want to ask the question, or they can type the question in chat window?
Sir, is there any market here to buy this pyrolysis oil in Chennai?
It's only for furnace oil, sir. Pyrolysis oil without any upgradation is as good as only a furnace oil. Typically, its price will be 35 rupees per liter. It's actually a low value product, and typically in diesel gensets and those kind of stationary power applications, people may use it. But typically, branded engines and gensets may not really get the warranty if you use these kind of fuels.
Okay, thank you, sir.
Is there any other question? Vishnu S. Nair has raised his hand. He can either speak or post the question in chat window, or any other participant if they have any questions regarding that. Sir, can you speak a little about your startup company, X2 Fuels?
Okay, so basically this is a startup focused on scaling up of technologies. Okay, so we are more into having worked a lot on the on different technologies. The idea is to basically scale up the technologies to a large scale, so large level, so that industries can different types of industries can basically use this for waste generation, or even it can be used for any agro residue management and things like that. So our startup company is based out of IIT Madras Research Park, and this is based on hydrothermal liquefaction technology. Okay, we actually we are the first ones to convert the batch scale process to a continuous scale process. Okay, in India, and even throughout the world, we are probably one of the few companies to really work at a large scale. So we have set up a 5 tons per day system, that is 5 tons of waste processing per day unit in Chennai, which will convert any kind of solid waste. Currently, we are basically on a test phase wherein we are using different industrial waste, we are using biomass waste, and so on to make oil, and we are really benchmarking the quality of the oil that we get out of this process. And we find that there is a very good promise because the oil quality is very similar to hydrocarbon, let's say crude oil, marine fuels, and so on. So which process is economical, whether pyrolysis or okay, so that's a good question. Again, I would say I would answer this question from a feedstock viewpoint. Okay, if your feedstock is exclusively plastics, okay, 100% plastics, then I would recommend pyrolysis process. Okay, but if your feedstock is anything other than plastics, okay, be it biomass, agri residue waste, biogenic biodegradable fraction or organic fraction of the municipal solid waste, microalgae, macroalgae, right, water hyacinth, right, for all these feedstocks, HTL is better. But pyrolysis is better because it is simple and you can actually get pyrolysis oil from plastics. Typically, olefinic hydrocarbon plastics can be seamlessly converted to the oil fraction through pyrolysis process. So it is dependent on the raw material. So pyrolysis is good for plastics. Manish Kumar, you have a question?
Hello, sir.
Yeah.
Sir, as you said that to use plastic as a raw feed in a pyrolysis is beneficial.
Mhm.
So, sir, basically most of the pyrolysis plant runs on a heater. On a heating limit is a heater, electricity heater. So
Yeah.
how economical it will be to convert plastic waste into the in a fuel? What it may be some maybe bakes, some maybe the automobile fuel.
Right. So
Some
if you see, typically, if I understand your question right, pyrolysis is an endothermic process. You need to supply energy. Okay, based on the price, based on the cost point, typically on a larger scale, I mean, gas-fired systems are easier because natural gas is cheaper as compared to electricity. Okay, so typically natural gas-fired systems are used to heat the plastics, and of course, you will get different fractions, waxy fraction, you will get a light oil fraction, heavy oil fraction, and so on, right? And that is where tuning the process parameters becomes very important. Okay, based on the type of plastic, if you're typically you will get a lot of wax when you use high density polyethylene or low density polyethylene. That is when you end up in a lot of wax in the oil. Okay, so at that point in time, we need to really understand what is the raw material, and based on that, you need to control the temperature of the process. Maybe slightly higher temperatures can actually crack the waxes better, and you can get more amount of low molecular weight hydrocarbons in the gasoline and diesel range. Okay, even from plastics. So tuning the process conditions is also going to be one important step.
Thank you, sir.
Thank you.
Is there any other questions?
Sir,
Yeah, please.
sir, is there any plant which runs on solar? By means pyrolyzer?
Yeah, there are some small scale pilot installations, I understand. I don't know exactly where they are, but this is also an upcoming topic. Okay, using solar thermal energy to run pyrolysis process. That is actually a good option. So you can actually, I mean, that's basically from an energy conservation point of view. That's very much possible.
Good. Thank you, sir.
Thank you.
If there are no further questions, we will wind up the session, sir.
Yeah, sure. Thank you. Thanks to all for your questions and participation. Hope the topic was interesting and useful to in the context of in the context of this program.
Sir, I request will you share your PPT slide of this session, sir, to us?
Yeah, I can share that.
Thank you, sir. Thank you for your wonderful session, for covering all the aspects. It's sustainable engineering and neutrality related to that topic. Thank you, sir.
Thank you. Thank you all. I'll sign off. Thanks.
Participants, please fill the feedback form that is posted in the chat window as well as in the WhatsApp group. We'll see tomorrow at 6 o'clock. Thank you all. Thank you for your patient listening.